Hello, everyone, and thank you for joining this session. My name is Alexey Vasilyev, and today I'm excited to present our work about item called start. Let's start with the problem. In sequential recommendation, everyone knows about state-of-the-art algorithms such as SASREC or BERFOREC, and they are designed to predict user next item based on their sequence of previous interactions. These methods work well for popular items with lots of ratings or clicks. However, they perform poorly for new or rarely seen items because the model cannot learn good representation for them. This is so-called cold start problem with items. It limits recommending new items or using them in a user's history to predict future interactions. And which is a standard solution of this problem. A common approach to this issue is using content-based information, but fortunately, real data sets, almost all, have this data. For all items called and warm, we can use information like product description or audio features or pictures maybe to generate embeddings and initialize by them the embedding layer of the backbone model. But here the catch, we have two options. If we keep the embeddings frozen, they don't adapt to the collaborative signal. As a result, recommendation quality suffers. But if we let the model train them, they drift away from their original content features, while cold item embeddings remain in the original space. And we got poor quality prediction in cold start cases. And we decided to combine both approaches, and our solution is here on the slide. For every item embedding, we combine two parts. The first part is frozen. It's you see on the slide here, content-based vector that never changed during training, since content embeddings can be quite large, and we use PCA transformation for dimensionality reduction. And also we are normalized getting content embeddings. The second part is a small trainable correction with its length strictly limited. This means the model can adapt to interaction data, but not move too far from the content meaning. And more formally, we try to limit the trainable correction length, it's a D vector, to delta. In this case, the minimum cosine similarity will be no less than the square root of 1 minus the square of the delta. This balance let us combine both content and collaborative signals, especially for new items. The adjustment is controlled by a single hyperparameter which bounds the correction norm. And you see that in this case, new corrected vector E, not so far from original vector C. And which experiments set up? We tested our method on 3 data sets. I told that in industrial data, we have a lot of data sets with description or something else content data, but in academic data sets or open source data sets, not so many data sets with this data. And we use Amazon M2 from KDD Cup, which includes e-commerce products and product description. Beauty, it's a classic data set with user reviews from Amazon, and Zvuk, music recommendation data sets with audio-based representations. On the slide, you can see the splitting protocol. We used global time splitting as a more correct approach based on another our paper, which will be discussed later in this section, and it's printed also on my t-shirt. And you can scan QR code. And our result, we use baselines, is a content-based KNN model, SASREC model with cross-entropy loss, incapable of handling cold items. Also SASREC initialized with content embeddings, but allowing full fine-tuning, and our method with trainable delta. We measured hit rate and NDCG at 10 on 3 groups: cold items, never seen in training, warm items, and all items. The results are clear. Our proposed solution consistently performed all baselines on cold items, sometimes by large margins. And overall and warm item performance was either slightly improved or at least maintained. There was no significant trade-off. We also found that the correction vector norm plays a critical role. Too small means no adaptability. Too large, and the cold start advantage is lost. We find that the values in the range 0.3 or 0 to 0.6 provide a good trade-off, giving the model enough capacity to learn while still keeping the embeddings closer to their initialization. In this case, minimum similarity about 0.8. Yeah, it's really close to original embeddings. Furthermore, we tested how recommendation improve depending on the proportion of cold items in the user history, and concluded that with a small proportion warm items, our approach shows significant improvement. Our trainable delta approach demonstrates improvements for rare items, with performance gradually converging to SASREC levels as item frequency increases. Upper graph shows absolute values and lower shows relative NDCG to SASREC. In summary, our work shows that proposed method adding a small trainable correction to a frozen content embedding consistently improves cold item recommendations while maintaining quality for others. It's simple, effective, and ready to be adopted in transformer-based recommendation system. The main downside here is increased memory use. Each item needs to store 2 vectors instead of 1, which could be a challenge for huge catalogs. Future work could address this issue. And you can read the article and repository on the QR codes on the screen. And thank you for your attention, and I'm happy to answer any questions.
I'll start with one question. It is related to the delta max that you decide. Okay, there you can control the amount of trainability, let's say, that you get. Have you thought about the idea of making different deltas or different amounts of trainability for each dimension?
Yeah, it's an interesting question. Really, we don't thought it, but I think if you have less parameter, it's better, because it's like you know, you could not overtrain.
Okay.
Yeah,
okay.
Maybe, yeah. And I think if you have a lot of data, yeah, you need find all of them. It's hard, I think. Yeah, but I think we try that. Maybe not for all dimension, but you can maybe part for some parts, 2 or 3 delta. Maybe, yeah, it's better.
I have another very, very brief question. This is related to the graph that you showed, in which you told us that for low values of delta max, you had an improvement for the matrix, but overall degradation.
No, for overall degradation, it's almost not. Yeah, because you see that. Okay. Really, you have a small improve overall,
yeah,
or almost the same like for SASREC.
Okay.
Or SASREC with content initialization. Yeah, but if you look on the cold items, you see that big improve. Yeah.